The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, this is a discussion of vibronic coupling and with particular relevance to formaldehyde. I've given you two papers. One paper is Keith Ennis's special model for vibronic coupling in formaldehyde, which is really a beautiful treatment. And the other is this famous paper on vibronic coupling, or the Crude adiabatic approximation, from the Journal of Photochemistry and Photobiology. And it is the basis for Pat Ficcaro's lecture, which is attached to the back of the lecture notes. And it is really complete and beautiful, and even though the journal has biology in its title, this particular article is very worth studying. Okay, so let me just begin with what we saw in formaldehyde last time. We saw that a transition which was electronically forbidden was observable because of mixing with another electronic state through a promoter mode, which was the out-of-plane bend. And so certain transitions were, well, the origin band was forbidden, and the vibronic coupling did not turn that on. But the vibronic coupling made observable half of the vibrational levels in the out-of-plane bend. Sort of as a separate thing, I discussed the spacing of the vibrational levels and said that was indicative of a symmetric double minimum potential. So there's two things which are going on, and it would be really, really beautiful if these two disparate things could be produced by the same, by one mechanism. And that's what Keith Ennis's paper is about. And I will end this lecture attempting to explain how this works. But it's a beautiful example of nature being careless and creating an observable situation which is far more confusing and complicated than the reality one uses to explain it. That in some sense the deperturbed model, the model that captures what is observed, is more beautiful and more simple than the actual observation. We're short one set of lecture notes. 1, 2. Yeah, I guess we are. Sorry about that. Okay, so let's just begin with the way in which we approach vibronic coupling. We start with what we call the crude adiabatic basis functions, where J is the electronic state and T is the vibrational state. And these are functions of electronic and nuclear coordinates. And we think of them as a zero-order electronic state where the electronic wave function is determined at the equilibrium position of the electronic state. And that we're not going to allow the electronic wave function to change as the internuclear distance changes. And we have the crude adiabatic vibrational state, which does change internuclear distance. So we have a wave function which is valid over all, which is defined as a function of R and Q without restriction. Yet the electronic wave function itself is restricted to a particular value of the nuclear coordinates. And then we have vibrational wave function. So this is the crude adiabatic approximation. And it is the way we normally think about electronic states. We think about electronic states as existing in having an electronic potential energy surface. And we have the different vibrational levels, and they do their thing, and we associate them all with one electronic wave function. We don't want the electronic wave function to change with nuclear positions. We know that's ridiculous because if the nuclei move, they have to carry the electrons with them in some sense. But the way we think about molecules is that they have an electronic wave function, and that's equivalent to the name of the state, and it's not going to respond to the nuclei. Of course, we have to fix this. This is an approximation. This is the way we think, but we're going to go beyond this point of view. Okay, why do we do this? We need to define a complete set of basis functions. And so the complete set of basis functions reflects the way we think about the problem, but we're honest people, and the reason we create a complete set is that we're going to attempt to describe reality using it. And so we always go beyond the approximation, the crude adiabatic approximation, that enables us to write an explicit function. So how do we go beyond that? Well, we have to write a Schrodinger equation. I mean, not only how do we go beyond it, how do we get these things? You know, how do we get these wave functions? I mean, it's all very nice if you write things on a blackboard, but somehow you need to be able to not just formally determine the functions, but actually determine functions. And so we write a Schrodinger equation. So it consists of several terms. The nuclear kinetic energy term, and then this is simpler than it seems. This is the potential energy of bare nuclei. Okay, now they don't have to be completely bare. They can have core electrons, but formally they are bare nuclei. And then we have the energy for the minimum of the jth electronic state, or the jth electronic state at this reference value. So this is an energy that's calculated by picking Q0, and that's an electronic energy. And then we have a catch-all of almost all the other stuff. So we have an electronic integral Yeah. I just want to make sure I got everything here. And so this is the Hamiltonian. And okay, so this is now the electronic expectation value of this operator that says, okay, let the nuclei move through some kind of correction. So this is the change in interaction between the electrons and the nuclei, and between the electrons and the electrons. And this is all formal. So this then is the Schrodinger equation, the Hamiltonian. I ran out of room, and so we want to be able to find the vibrational wave function. So this is all multiplying the vibrational wave function. So the Tth vibrational wave function for the jth electronic state, crude adiabatic approximation, function of Q, and that's equal to the energy of that level chi j t q crude adiabatic. So this is the nuclear Schrodinger equation that we use to determine the energies and the wave functions. So this is a simple thing. This is a simple thing because bare nuclei, well, they're point charges. You can calculate what they are. This is an electronic energy that you can calculate ab initio, or you could just parameterize. And all of this is the complexity. Yes?
So then this is an exact expression.
No, it's not quite exact, because how are we...
That sort of takes care of...
Well, but I mean, we are somehow attempting to represent reality by fixing things at some equilibrium geometry. And so we're going to want to go beyond this, but this is formally how we define these things. Okay, it's all kind of a circular argument until we actually start reducing things to fit parameters, and you'll see. Okay, so we want to go beyond this. We want to define wave functions which are not so artificially restricted. So we use perturbation theory. So here is a wave function which is beyond the crude adiabatic approximation, and it's equal to the crude adiabatic wave function, and then some correction terms. And so we're doing first order correction of the wave function. So we're going to have other wave functions. And some mixing coefficients in here. So the usual thing, we have the original wave function, the zero order wave function called crude adiabatic, and then other crude adiabatic wave functions with mixing coefficients. And the mixing coefficients always have an energy denominator. Okay, always the state you're starting with minus the other state. So these are zero order energies. And then we're going to have a coupling matrix element. Now we've got nuclear coordinates and electron coordinates and both. And so we need a notation that says, what are we going to integrate over? And so we'll use curly brackets to indicate we're integrating over both coordinates, ordinary angle brackets for electron, and parentheses for nuclear. That's in fact right. Okay, and so we have an integral, which will be the vibronic JTCA delta U KR CA. So this is an integral of between crude adiabatic wave function. This is the correction term. And of course, we still don't. This is just moving things around. We haven't learned anything yet. What we're going to want to do is to say, okay, how do we describe this? And we're always going to be expressing things in a power series in the nuclear coordinates. And we're always going to throw away all but the lowest order, all of the higher order terms, keeping only a term that is going to give us a logical structure we're going to use. Okay, so we replace these things by the product that they symbolize. Okay, so that's just a replacement. That's what this is. And then we're going to re-express this. So we're going to have a sum over all electronic states other than the state we're starting in. And then we're going to have a sum over all vibrational levels in that state. And then we'll have a vibrational wave function. And then that vibrational wave function is part of an integral over an electronic function. Okay, so we have now the electronic matrix element. So this electronic matrix element is a function of Q. And then we have Crude adiabatic JT. Yeah, that's right. And I just have to get this notation right. Okay. And then we still have the same stuff in the denominator, JT, adiabatic. So you're already remembering the first rule of Bob. Never listen to me do a derivation, especially if you don't have the notes. Okay, so we're continuing now. So we have an integral over the electronic wave. This is the operator in question. This is an electronic integral. This is going to be expanded in a power series. And so we'll have a derivative term, a derivative of this correction with respect to each of the normal coordinates times the normal coordinate, which will be acting here. So this is all a formal reduction here. Okay, so, I still don't have a wave function. So this all is multiplying. This is the mixing coefficient that multiplies psi k 0 r q 0 k r crude adiabatic q. Okay. So the next step is to simplify this. And this expansion of the wave function is called the Hertzberg-Teller expansion. It's famous. Hertzberg collaborated with Edward Teller, and this was one of the beautiful things that Teller did. Okay, so now let's use it. So we now have this delta U of R and Q, and we want to expand that in a power series about Q0. And so we start out with delta U R Q0. We're expanding about 0. But of course, by definition, this first term is 0. Okay, and then we have the linear term, the partial derivative of, it should be delta U, but we're just calling it U, of RQ dq and the nth normal mode. This is the sum over the normal modes. Yes, Josh?
Can I just ask you a question about the...
Yes?
You don't have the electronic energies anywhere in there. The energy denominators are only the vibrational state energies that come from solving the Hamiltonian that you listed before. The epsilon sub j's are not in there, but you're mixing states from different electronic states.
They should be there. These really are differences in energies overall between...
So that's not the same ECA that you put previously. Right, so that ECA there at the bottom of the top board, that's not the same ECA that's in the energy denominator. Yeah, in other words, you're missing that thing you're pointing to right now. Down here on the bottom board, it should be in those energy denominators.
This is the total energy.
Oh, okay. Okay.
Okay, so I think it's okay.
Yeah. Yeah.
All right. There are places in the notes where I think factors disappear, never to be heard from, but this is not yet one of them. Okay, so we want to deal with this so that we can at least massage this into a form that we can see qualitatively how it enters into the structure of the problem, and we start defining parameters that become fit parameters as opposed to things that you would calculate de novo or ab initio. You could calculate these things ab initio, but really this is designed to create a model for what you observe, which is expressed in a formally complete sense, and which has a few adjustable parameters which have definite meanings, but we would derive those parameters from a fit to the data rather than from a calculation. Okay, so we have a first derivative term times the displacement from equilibrium for the nth coordinate, and then higher order terms which we are going to throw away. Unless it's not good enough and you have to go to higher order. And so, but usually when you do a vibronic coupling calculation, you keep the lowest order terms, and sometimes you have a special name for a calculation where you have to keep higher order terms. And for the Jahn-Teller effect, there's an ordinary Jahn-Teller and a dynamic Jahn-Teller, and I believe that corresponds to the next higher term. But the important thing is the structure of this problem. Okay, so we have this expansion of the evil term in there, and so now we can write the wave function as the zero-order wave function at Q0. So this is the zero-order function, and this is, we're going to write a correction to it, and that correction comes from now k not equal to j, sum over all electronic states, sum over the vibrational levels of that electronic state, sum over the promoting mode. And now we have gamma n j k r j t psi 0 k r q 0. So this is just a mixing coefficient. We've just condensed a whole bunch of garbage into this times k so we're writing our wave function as itself, the zero-order term, plus a bunch of corrections, and all of those corrections are controlled by this mixing coefficient. And the mixing coefficient is defined, I should have written that, so K R J T N, and that's not a power, that's just which mode is given by the it's just this thing here. Okay, so now from the structure of this problem, so this thing has to be different from 0. Okay, so I'm getting ahead of myself. So we have the first correction term. It involves a derivative with respect to the nth coordinate and the nth coordinate. So the derivative has to be non-zero by group theory. The direct product of these two characters has to be equal to belong to the direct product of these two irreducible representations has to be the irreducible representation of the derivative term And so we're taking a derivative with respect to the nth coordinate. So the direct product of these two irreducible representations has to be the character of the nth coordinate. And we get a Q out of here, and Qn, and this, the direct product of these two vibrational wave functions, has to include the irreducible representation of the nth coordinate. So we have an electronic integral that has to be not zero, and a vibrational integral that has to be not zero. And the overall requirement is that gamma k cross gamma j must include, and I don't know whether I'm writing these symbols the right way around or the wrong way around, Qn, because we have a derivative here with respect to Qn. So this electronic, so, and we then have gamma r cross gamma t. That also must include gamma Qn. That can be condensed to gamma k r cross gamma jt must include totally symmetric. But Qn is not totally symmetric. So we have that the two coupled wave functions must be the direct product. Their direct product must be totally symmetric because the Hamiltonian is totally symmetric. But the coupling mechanism has to be via a non-totally symmetric coordinate. Okay. So that's the formal theory, and now let's try to apply it to a specific example in order to see how beautiful it is and how it helps us to make sense of amazing stuff. So we're going to come back to this, but Keith Ennis's model. Keith Ennis was was often called the dean of polyatomic molecule electronic spectroscopy. He was a wonderful man. I knew him very well. He went out of his way to help me when I was beginning to do formaldehyde experiments. And he spent a sabbatical at MIT. And yeah, there are just a series of great spectroscopists that I've had friendships with. And Keith was really one of the most amazing people. So what his model says is, let's take two harmonic potential surfaces and we're going to explain everything that is observed in formaldehyde by two harmonic potentials for the bend. And so this would correspond to the zero order structure of formaldehyde being planar. The energy levels tell you that it's not planar. But the group theory tells you it's acting like it's planar. But so he says, okay, let's take two identical potentials, harmonic, with minima at the high symmetry point. And all of the coupling comes from this partial of this correction term, that first, all of this, and with this model saying two harmonic potentials coupled by this, identical frequencies, you get level staggering and intensities. So you're able to explain two classes of phenomena with a very simple model. And you know, it's similar to the way we look at diatomic molecules. We look at a diatomic molecule and we say, that's a good potential. That's a bad potential. We don't believe that. even if the energy levels are telling you that that's what the potential is. We believe this, and any departure from that shape is somehow nature screwing up. And that's a very arrogant point of view. But if you can create a simple model that makes sense of not just one thing, but two disparate things, you begin to think, well, nature really did screw up, or is hiding from us the beautiful truth, which is that the potentials have the right shape, but there's just a coupling term. And one kind of coupling term and one coupling mechanism enables you to recover everything that you observe. That behind complexity, there is beautiful simplicity. And that is an attitude that I got very much from Keith Ennis. There were other spectroscopists who loved the complexity and said, well, I don't care, I can deal with this. But Ennis felt somehow, as I did, insulted by the complexity and felt he had to win by creating a model which was simpler. And I think that, you know, if anybody gets what I have to offer, it's this idea that there is a simplicity behind whatever nature throws at you, and that your job is to find it. And so this is really, you know, a beautiful example of how you try to do that. Okay, so let me just continue with some of the formal theory before we get to Ennis's model. So let's go to page 5. So since we talked about what is the mechanism by which acetylene can borrow intensity, I'm going to just assume that we know this. And so we're going to look at two electronic states, the singlet B2 state and the singlet A2 state. These are two excited states. This is the first excited state. And we're going to just look at the outer plane bend in both states. So this is the outer plane bend is mode 4, 0, 1, 2. And these two states have different symmetries. A2 times B2 is B1. And it's the B1, this mode has B1 symmetry. And so the B1 mode, the outer plane mode, has the right symmetry so that A2 cross B1 is equal to B2. And so the distortion of the molecular geometry from planar by this outer plane vibration mixes in some electronic character of this B2 state. And so we want to build a model that shows how this can be done. So we write the wave function for the A state and the nth vibrational level of the A state. And that's going to be equal to the zero order contribution for the A state evaluated at Q equals 0. The crude adiabatic. So here is just, I've just written the product of the electronic times the vibrational. These are the zero order functions. And then we're going to have a sum over levels of the B state, psi 0, chi B prime, crude adiabatic, and then mixing coefficients. So the mixing coefficients have the form B V prime, A V, and a little n up here indicating which mode. Okay, so we're writing the wave function as the zero order function times an expansion over the other state and mixing coefficients. And we know what this mixing coefficient is formally. So let me just write that because we're going to need to use the selection rules for vibrational wave functions that come out of this. So we have gamma is equal to an electronic matrix element psi b0 partial of u with respect to q4 evaluated at equilibrium psi 0a, let's put the twiddle on it, and then so this is the vibrational, so we did a power series, and so this is the electronic integral, and that's multiplied by Q4, and we do the vibrational integral over that, and we have the energy denominator, A V4 minus B V4 prime, and little twiddles, and we call these crude adiabatic. Okay. So this is the mixing coefficient that we need, and if we say that these two electronic states have the same bending potential, we are free to do this, especially if we don't know anything about this state or don't need to know anything. We can just say, well, there's some other state that acts as if it has the same vibrational frequency. What would happen? And if the real state doesn't, well, then you could correct again. But you always want to choose the simplest possible model. So here we have an integral of the harmonic displacement coordinate, and this has selection rules, delta V of plus and minus 1. And so it has selection rules, delta V of plus and minus 1, and it has a factor. By making this dimensionless, you know that it has a factor that's related to 1 over the square root of the vibrational frequency for that mode. And this, we also know, this is the difference in energy between the minima plus the difference in energy. So we have the difference in electronic, well, let's just write it this way. TA plus omega VA minus TB plus omega VB. Okay, and so we have TA minus TB plus omega times VA minus VB. Okay, and so that gives us the mixing coefficient. So there's a lot of stuff that comes in. Now, we have selection rule. V4 prime can only be one larger or one smaller than V4. And so we can write the wave functions, psi A V4, as the zero order term that we know plus beta psi B 0. Beta is just it contains all of the stuff that's that we don't know or that we want to treat as a parameter times V4 square root chi CA B V4 minus 1 plus V4 plus 1 square root chi CA B V4 plus 1. Remember, the matrix elements are always the square root of the vibrational quantum number for the larger value. And so that's why there's a little bit of asymmetry here. And we can write the wave function for the B state prime as basically the zero term, and everything is more or less the same except we have the opposite sign because the sign of the energy denominator is reversed, and we have different things that go in here. Okay, so if we have now our wave functions corrected in this simple way, we can then calculate the intensity of transitions. I'm going to have to erase some boards. So we have an electronically forbidden transition from the X state to the A state. We know it's electronically forbidden, and so the zero order term in here is going to be irrelevant. So we want to calculate the intensity of a transition to the A state, the V4 prime level of the A state, from the X state, the V4 double prime level. So prime and double prime here are just lower state, upper state. And that's always going to be given by, or it's going to be proportional to, the square of a transition matrix element. So psi A V4 prime, transition moment, psi X V4 double prime, quantity squared. Okay, and so now we put in all of this good stuff that we had worked out for the form of the wave function. And we don't care about this, we care about that, because this is the B state. We can go from the X state to the B state. And so we're going to have a matrix element from the X state to the B state, and we're going to take the square of the matrix element, and so we'll get a factor of beta squared out in front. So beta squared, and then we have the squared terms, well, I better write it this way. Okay, so we have psi b 0 mu b, because it's a b-type transition, psi x 0. So this is just the electronic transition from the ground state to this other state, times now the vibrational factors. We have V4 square root, overlap between B, V4 minus 1, crude adiabatic, X V4. Now, we haven't made any assumptions about the form of the vibrational wave functions for the X state relative to the A and B states. The A and B states have the identical potentials in our model, but the X state can be anything. So this is a vibrational overlap integral that we would calculate. And then we have the other term, V4 plus 1 square root times adiabatic B V4 plus 1 X V4. And so we're going to be taking the square of that. Okay. And so when we do that, we get beta squared. And we're going to have squared terms and cross terms. So the squared term is just going to be V4 times Q, the Frank-Condon factor for B V4 minus 1 X V4. So let's just put the X up here. So that's a Frank-Condon factor, which we'd calculate just for one, for the two states. And then we have V4 plus 1 times QBX, another Frank-Condon factor, B V4 plus 1 X V4. So those are the squared terms from here, and then we have a cross term. Now the squared terms are both positive. The cross term can have either sign. So we can have constructive and destructive interference. So the cross term, there's two of them, and we have V4 plus 1, and then we have two overlap integrals, V4 minus 1, V4, and V4 plus 1, V4. So double prime. Okay, so this is the whole story. This term, because there are two vibrational overlaps involving a common initial state, but two different values of the upper state. This is the transition to a particular vibrational level of the A state. So this intensity is governed by three terms, two positive terms, Frank-Condon factors for the other electronic state, and then this peculiar cross term. Okay, now we have to remember that the B state is a singlet B2 state, and the transition is it singlet B2 or singlet B1? Doesn't matter. A2 times B1. Okay, it is B2 from the X singlet A1 state. This is an electronically allowed transition. Mode 4, nu 4, in both states is non-totally symmetric. So that means that if you have an allowed transition, you can only have transitions between vibrational states of the same symmetry. So you can only go even to even or odd to odd in mode 4. So if we're starting from V equals 0 of the ground state, we can only use even quanta of the B state. And the even quanta of the B state only talk to odd quanta of the A state. So this vibronic allowed mechanism says if we're starting from the ground state, we're only going to see odd quanta of the A state. Or if we're doing a hot band from one quantum of mode 4 in the X state, we'll only see transitions into even quanta of mode 4 in the A state. Well, this is perfectly okay. That's what we saw last time. This is what we expected. Okay, but now these are Frank-Condon factors that involve all modes. And so we can factor out the intensity is going to be beta squared times Q Bx, let's call it all modes except nu 4. So these are products of squared vibrational overlap integrals involving all the other modes. And so from that point of view, we have a transition that involves Frank-Condon factors, but those of a different electronic state. And then we have an electronic matrix element, MB, bx squared. And because this is B type, that means that there's a factor from that controls the rotational transitions. The rotational transitions express the transformation between the laboratory and the body. And so this is going to control the selection rules for the rotational transitions. And then multiplying all of this, we're going to have a, so in my notes, I wrote this as a product of individual mode Frank-Condon factors, but we can just say they're all one. And then we have this sum over V4B, VA mode 4, Q4, V4B, VB, V4X. Okay, so this is coming from the vibronic coupling mechanism. This would reduce to something simple if the frequencies in the A and the X state were the same. And then we have a vibrational overlap. And we're summing inside the square. And the square is, that didn't get lost there. It got lost earlier in the notes. And so we're going to have two paths that interfere. So this is the overall structure of the problem. So if you are going to do vibronic coupling calculations, these are all the things you manipulate. And the surprising thing is that you have Frank-Condon factors that control the transitions to individual vibrational levels, which are those appropriate for the non-promoting modes, appropriate to the other electronic state. And then there's stuff in here. It's usually two terms. And they're the square modulus of two terms, and they can interfere constructively or destructively. So that's the overall pattern for the intensities. Now, qualitatively, what does it do to the energy levels? Page 8. So this is an Ennis-like model, but it's qualitative. Suppose now we have two zero-order potentials, and we're only looking at the promoting mode symmetry. And so we're interested in what is the matrix element as a function of the non-totally symmetric coordinate. Well, there's no matrix element between these two potentials at equilibrium, by definition. The farther you will get away from equilibrium, the larger the matrix element is. So what does that do? Well, it's a two-level problem, two-level, not in a vibrational sense, but in an electronic sense. The one gets pushed up, one gets pushed down, equal amounts. And so what you end up discovering is that this potential becomes narrower, and this potential develops a double minimum structure. Better be careful. Double minimum structure like that. So this is just a natural consequence of two levels interacting, one being pushed up, one being pushed down. And it's possible that the interaction is too small to create the double minimum. It just maybe makes it broader. Maybe it makes it look flat-bottomed. But this one always gets narrower, and this one always gets broader and can acquire this double minimum structure. Now, you can say, oh, it's got a double minimum structure, then I'm going to get level staggering. So the same model enables you to explain the vibrational selection rules and the appearance of level staggering in the lower of the two interacting states. Okay. So now we come to the exact treatment. What time is it? Okay, we should probably stop pretty soon. The tricky thing, so on pages 9 and 10, there is a treatment of this problem. And the key equation is we have the interaction matrix element, which is given by sorry, this is not the interaction matrix element. This is the potential curve. And so the zero-order potential curve has this form. So omega squared is just k over mu. And so k, but these are mass weighted. So we're going to have a k, a force constant, over mass factor. There's going to be this mass factor out of here. And so that's just a harmonic oscillator potential. And then we have the second order correction of that. And so that's expressed in terms of this gamma parameter, qn squared, and so we have two different frequencies. And that just expresses how the energy denominator, how as you change Q, the different vibrational frequencies cause the energy denominator to change, Qn squared. And then we have the equilibrium position for the K potential and the equilibrium position for the J potential. So this is second order perturbation theory. Now the tricky thing is you want to expand this about Qn equals 0. And when you do that, you get a Q squared term and a Q fourth term. And no constant term, because at Q equals 0, this is 0. So there's a Q squared term and a Q4 term in the power series expansion. The Q squared term combines with this to give an omega prime squared, Qn squared. And the Q4 is going to give an alpha Q to the fourth power. And so that then enables you to describe the potential curves, the perturbed potential curves. And the upper one has this modified quadratic, modified harmonic potential, harmonic frequency. And they each have a Q to the fourth term with opposite sign. And then you can solve for the vibrational levels of these two potentials, assuming the zero-order potentials are harmonic, and you get all of this stuff that I said you would. And this is Ennis's model. And so for formaldehyde, Ennis was able to account for everything given fit parameters where he had the difference in energy between the B and A states. He used the harmonic frequency for modes 4 equal, and he had a coupling term. And that coupling term, and so with these three parameters, he was able to account for everything, the intensities and the level patterns observed in the A state. And this is just a remarkably simple model. And I'm pretty sure that the energy for the B state relative to the A state also corresponded to reality. The observed B state, I've got that in the notes here somewhere. The B state is 3.6 electron volts above the A state, and 3.6 electron volts is pretty close to 28,000 wave numbers. So not only did this model with 3 parameters account for everything observed in the A state, it corresponded to something that was semi-realistic. So anyway, that's a neat model. I'm sorry that, you know, it's concealed by all these equations, but it's such a simple thing. You say, we got one mode that's doing the job. If we need to, we'll make the frequency of that mode the same in the 2 interacting states. And then we just do perturbation theory. We diagonalize the 2x2 problem for the 2 potentials. We get potential curves. And then we do second order perturbation on that, and we get the energy levels and the intensities. It's really incredibly beautiful.